welcome to our talk, which we decided to split up between Frank and me. So let me begin by shortly introducing myself. My name is Ralf Palutke, and I'm here for the Friedrich-Alexander University of Erlangen-Nürnberg, where I am part of the IT security research team. As for today's talk, we want to give a brief overview of several new anti-forensic techniques that allowed us to hide process memory from state-of-art memory forensic and live analysis frameworks. Let me begin by motivating the topic. As of today, malware still appears as the empowering technology for digital cybercrimes. And over time, malware samples even significantly increased in sophistication. As a consequence, analysts began to rely on memory acquisition as well as live forensics to detect and analyze these malware samples. On the other side, malware authors began to incorporate anti-forensics, which aim at subverting certain kernel data structures typically used by analysis tools and allowing to tamper with the memory acquisition process or subvert live forensics. So our work aims at advancing this arms race between malware authors and forensic investigators. To summarize our contribution, we developed 3 novel subversion techniques for hiding process memory from memory forensic and live analysis tools. And to prove practicability, we provide proof-of-concept implementations for both Windows and Linux. In addition, we extensively evaluate our approaches and found that both volatility and recall fail to detect these hidden memory ranges. Lastly, we provide several recall plugins that are able to detect our anti-forensic techniques. To allow a better understanding of our design principles, we first provide a brief overview of some technical fundamentals. We start out with memory paging, a mechanism provided by modern operating systems to establish a virtual abstraction of a machine's physical memory. Basically, the physical memory is structured in so-called page frames, which can be referenced by their page frame numbers. And with the help of the concept of virtual memory, each process expects to own the entire physical memory alone. Similar to the physical memory, also the virtual counterpart is partitioned into equally sized chunks, now called pages. In order to translate virtual pages into their corresponding page frames, a hardware memory management unit traverses a per-process-based page table hierarchy. Each of these page tables contains entries which include memory access permissions to determine which types of accesses are permitted and which lead to a page fault subsequently handled by the operating system's kernel. The virtual memory can further be divided into a kernel and a user space, whereas the kernel space maps the actual operating system's kernel, while the user space maps a process's memory. Whenever a program is loaded from disk to memory, its sections, including code, data, and so on, are bundled into several segments. These segments are described by memory area structures, which appear OS-specific. On Linux, for example, these memory area structures are called virtual memory areas, or short VMAs, while in Windows, they are called virtual address descriptors, or VADs. Lastly, I want to shortly talk about shared memory, which, as the name suggests, describes memory that is shared among multiple processes in order to allow the exchange of data. While there are different types of shared memory, we focused on anonymous or page file backed shared memory for this work. Typically, shared memory is accessible until no process has a handle to it anymore, whereas private memory is mapped into only one process and thus is lost after the owning process unmaps it. To create a shared memory segment, operating systems usually provide dedicated APIs and store referencing handles within all kinds of kernel data structures. So with these fundamentals in mind, I now want to introduce our anti-forensic techniques. For a quick overview, all of our techniques are capable of hiding parts of process memory and can either be used independently or in combination. Our attacker scenario comprises a process that intends to hide malicious parts of its memory, either being launched or infected during runtime. The malicious memory per se could contain injected shellcode, dynamically loaded libraries, or simply parts of the original application. Our first technique is based on the remapping of certain address ranges, which are referenced by the previously mentioned memory area structures. So assume the following base scenario depicted by the graphic on the right. We have the process address space, including several memory segments like the actual executable, a shared library, as well as a third area that contains both benign and malicious code. Each of these segments is described by a corresponding memory area structure, typically containing information about their virtual start and end addresses, as well as some access permissions. And as many forensic tools rely on the integrity of exactly these data structures, manipulating some of their information allows us to hide certain address ranges. Specifically, one can modify the virtual start and end addresses of the memory area structure that references the address range containing the malicious memory. There are different ways to perform this attack, however. Looking at the example on the right, the relevant area contains both benign and malicious content. So an adversary could simply alter the end address of the corresponding memory area structure to exclude the malicious range. And the nice thing about this technique is that memory area structures are typically not consulted once they have been set up. So a processor is able to access the respective memory despite being excluded in the memory area structure, as the underlying page table entries are still intact. So there's no need to restore these modifications to access the malicious memory. Our next technique does not even require to modify a process's virtual memory layout, but it directly manipulates the underlying page table entries. As a base scenario, we assume two physical page frames, one benign, shown in green, and one malicious, depicted in red, each referenced by their corresponding page table entries. In order to hide the malicious page M, we need to find the respective page table entry by manually traversing the page table hierarchy of the respective process. To determine a relevant virtual address range, memory area structures could also be consulted here. The modification itself requires kernel privileges, and compared to the previous technique, those modifications must be restored prior to accessing the malicious memory. Otherwise, the process will fail to access the correct content. In the next two slides, I present two possibilities to implement these PTE modifications. The first approach remaps the malicious pages to an equal amount of benign page frames. So in our example on the right, we remap the page frame number of the malicious page M to reference the benign page frame B. Consequently, we have now multiple virtual addresses that do resolve to the same page frame B. Also, we could choose any page frame in the system as a redirection target. We should pick frames that contain similar content, meaning code pages should be remapped to code frames, data pages to data frames, and so on. This is because an analyst looking at a code page usually expects to find code here. Besides remapping a page table entry, we could also entirely erase or nullify them. Then, these entries appear like they have not been initialized or accessed yet, or are simply not present at the time. Note that solely invalidating the present flag of a page table entry is not sufficient, however, for hiding the malicious memory, as an analysis tool could still detect the remaining information and try to rebuild the entry. So in summary, PTE Erasure prevents tools from establishing a correct correlation between a frame and its corresponding process. For this technique to work, we also verified that both Linux and Windows do not rely on page table entries to find free memory. So there's no risk of being freed or reused by the operating system during the time of the entry being nullified. Our last technique subverts shared memory mappings by making use of the fact that shared memory does not have to be shared between multiple processes, but instead can be solely used by only a single process. In contrast to the two previous techniques, shared memory subversions do not even require kernel privileges, but can be used by an unprivileged attacker. So on this slide, you can see a similar graphic depicting the process address space with several memory segments. For the purpose of explaining this technique, we simply differentiate between private areas, pictured in black, and a shared area, which is illustrated in red. To actually set up a shared memory area, the following 4 steps are required. First, the malicious process has to create a shared memory section and afterwards map it into the target process. It can then write malicious data or code to the newly created region and, as a last step, once again unmap it from the process's address space. While this removes the describing memory area structure, the kernel still keeps a reference or a handle in the process's task struct. To actually access the shared area, the process now has to remap the memory, for example, when executing encoded code, and immediately unmap it afterwards. The reason why this technique successfully hides memory from a wide variety of tools is that these typically focus on currently mapped memory only. So if the shared area is not accidentally mapped when running the analysis, these tools fail to detect the respective area. So this concludes the first part of our talk, and I now pass over to Frank, who will present the rest of our work. Thanks for your attention.
So let's talk about memory subversion detection. First, MES remapping detection. What we are using here are the paging structures. We are enumerating all the page tables and examining the page table entries. Each page table entry corresponds to a virtual address. And by examining the page table entry, we know which virtual addresses are currently valid, so they are referencing page frames that are currently mapped. And we can use this information to check whether or not they are virtual addresses which are not described by a VM area structure but are valid. So in this case, we have those 2 virtual addresses which seem to reference valid page frames, so there's actually memory content behind them, but they are not part of any MES structure, so that's something suspicious which we alert on. Now the PTE Subversion detection on Windows. It's on Linux different story, so we are splitting this detection in 2 parts. On Windows, we now have here the initial situation, so the malicious PTE points currently still to the malicious page. And in this case here now, we have also the physical point of view on the memory, the PFN database, which we mentioned earlier briefly. This is just more or less just an array of MMPFN structs, which are indexed by the PFN number. So the PFN here points on the one hand to the page frame, and to a MMPFN struct over here. Each MMPFN struct for a valid page also points back to the PTE that belongs to it. So we have here a kind of loop that points back and forth. So if we're now doing the PTE remapping, so we are changing the PFN value, the pointers get modified. So we are now pointing at the benign page down here, and we are also referencing another MMPFN struct. So that means we have a broken loop. We have a valid loop down here because this MMPFN struct belongs to a valid page, the benign page is already there. And we have a valid loop here. But we have also the pointer from over here, which does not point back over here. So this is something that we can detect on. Also, by enumerating all the MMPFN structs, we will encounter this one here, which points to this PTE, but the PTE does not point back. So this is also something that we can detect. And the third part here is the PFN number. So by enumerating all the PTEs and collecting all the page frame numbers, we can detect duplicates. And by that, the PTE remapping. This only works for shared memory, for private memory. With shared memory, this doesn't work because with shared memory, it's quite common that multiple PTEs point to the same page frame. Also, this detection here does not work with shared memory because for shared memory, those MMPFNs don't point to this PTE, but to the prototype PTE. So we don't have this loop that we can detect on. So these detections here only work with private memory on Windows. The detection that we will now see in a few seconds on Linux does work also with shared memory. Okay, Now the last slide for Windows. In this case, we see now our modified PTE remapping, because the original one, as I said, crashes when Yara is, for example, scanning the process. So this is the situation. The detection is more or less the same. Only the situation is a bit different. So we can see now here we have our PFN value, which points at the second page, which has been created for this PTE. So the also created MMPFN struct points back to this PTE. So this loop here is fine. It points back and forth validly, so there's nothing suspicious here. But there are two things to mention over here. At the one hand, we have again an MMPFN struct which points to this PTE, but this PTE does not point back. And also we have two MMPFN structs which point to the same PTE. So those are two characteristics that we can detect on. Okay, let's now look at Linux. The point of view on the physical memory on Linux are the page structures. So there are several page structures which are more or less also indexed by the page frame number. And by enumerating those, we can collect page structures which belong together, and also physical pages by that matter. This is done by looking at the mapping object that is referenced by those page structures. This mapping object is also referenced by the VM area structures. So by this mapping, we can correlate pages with their corresponding VM area structures. A little thing to mention over here, there can be multiple mappings per VM area structure. At the one hand, a mapping can be referenced by the F mapping, so this is the case for files that are mapped. And also in this case, there can additionally be the anon-VMA chain pointing to mappings. There can be multiple ones. This is especially the case when forking and when using copy and write protections, and then getting private copies being created. Those are then referenced by those mappings, so there can be multiple ones. That's just something that we have to keep in mind when investigating this issue, that we have to collect all of them. Behind those mapping is, in this case, for the anon-VMA chain, anon-VMA structs, and for the F mapping, it's an address space struct, but this detail doesn't really matter for us. The only thing that we are interested in is the object itself, which we can use to correlate the page structures with the VM area structure. So the fields of those mappings are not really interesting to us, just the object itself. Okay, now let's have a look at the other side. So when we are now enumerating the virtual addresses for a VM area struct, we can resolve them to the page frame number, and by that get the corresponding page structure. And again, we can collect them based on the mapping. And in this case, we have three virtual addresses with the three page structures which belong to this mapping, which also corresponds to the mapping for this VM area structure. If we are now looking at our attacks, in this case, the PTE Erasure, the initial situation is that we have our malicious page over here, which is still referenced. Now we are erasing the PTE. The pointer goes away, and when we are enumerating the virtual addresses, we now only get two pages, because this one doesn't belong to any page structure anymore, because it doesn't have a corresponding PFN. So when we are collecting those for this VM area, for the virtual addresses, we only get two pages for this mapping, or with this mapping. If we, on the other hand, enumerating all the page structures, collecting them based on their mapping, and then looking for each VM area struct for their corresponding mapping and the pages, we will see that we will end up with three page structures. So we can clearly see a diff, 2 on the left side, 3 on the right side, and this is something suspicious which we alert on. So, and the last step is our shared memory subversion detection. It's more or less the same on Linux and Windows. We are basically just enumerating all the shared memory handles and looking for those which are currently not mapped into the virtual address space and alert on them. On Windows, we are additionally checking for the executable permission. So we are only alerting on executable memory, because there would otherwise be a lot of false positives. On Linux, we are not checking for the executable state, because it's not a reliable way to detect this kind of memory. And hence, we also have some false positives on Linux, which we'll see later. We implemented our techniques for Windows and Linux, and tested those in multiple VMs for Windows and Linux, in both cases on x64 architectures. And this is those are the results for the memory forensics point of view. We used multiple plugins. We used Yara scan plugins. We used Rekall and Volatility for all those plugins. And what you can see for Yara scan, for example, is that Volatility's Yara scan was not able to detect any of our hidden malicious content, but Rekall did. The reason is that Rekall does a raw search, so it doesn't rely on any virtual address structures, virtual address translation structures. It only searches the raw memory, and by that he finds our hidden code. But obviously this only works if we know upfront what we are searching for, so it doesn't work as a generic method. We also had a look at some dumping plugins. So we dumped the memory content of the processes, and only in the case of the MAS remapping and only with volatility we were able to find our malicious code in there. With the other tools and other plugins, it was not the case. And also, we did find our malicious code by if we accessed it directly. So if we used Rekall or Volatility, the interactive shell, and did a read for the virtual address, in this case also it was possible to detect the malicious memory, but only in the case, again, for MAS remapping. And a third time again, with PTE num, we were also able to find our injected code for MAS remapping. But besides that, in all other cases, our malicious code was not found by any of those plugins. In some cases, there were some indicators that could maybe give you a hint about something fishy going on, but the actual memory content was only detected in those cases that I mentioned earlier. So from a live forensics point of view, it gets a little bit worse. On the one hand, we also used the tool Yara and scanned all the processes. None of our hidden memory has been detected by Yara. We were able to detect our malicious content in the case of MAS remapping again with the debugger, but only on Windows. So with the WinDebug tool, we were able to find our malicious content by searching and also by directly accessing the virtual addresses. But besides that, none of those approaches were able to find our hidden malicious code. We tried dumping the process address space with debug, with GDB, with WinDebug, also used Process Explorer on Gcore, but our malicious content wasn't in those dumps. But at least in some cases there were errors pointing out that some of the addresses seemed to be something wrong with them. So there were some indicators, but the actual memory content was only detected in those two cases for MAS remapping and not in the other cases. And also to mention, the shared memory scenario with shemget on Linux was not at all, in any case, in any way detected by any of those plugins or tools.
And addresses the first part.
Okay, let's have a look at the conclusion. We introduced 3 novel subversion techniques which successfully hide memory from live and memory forensics on Linux and Windows, and also corresponding detection approaches. We are also releasing proof-of-concept implementations for the subversion techniques and 2 Rekall plugins for the detection of shared memory subversion. Some of the limitations of our approaches are the blue screen regarding PTE subversion when the process exits. The details are explained in our paper, so this is still work in progress. Then the circumvention possibility of our detection approach on Windows with shared memory, and the false positives for shared memory subversion detection on Linux are also some limitations. The false positives are mostly related to the Firefox. There's also quite some future work left, especially the implementation and evaluation of our detection approaches, but also in particular testing the effects of the modification of everything that we've used for detection so far. So that's it. Thank you for your attention.